How you doing? I'm Mr. Rose, and today we're going to tackle a dynamics question from 1993 AP exam. You can see the question here. There's a car traveling to the right in the positive direction. Well, I'm going to define the positive direction, and they actually kind of define that for you here when you see this negative kV. This is a gamut of some easy and some difficult portions of a question. So what I'd like you to do is take a moment to take a look at the question, read over, grab some scrap paper, and start at it. I would also like you to take a moment to think to yourself, you might be 17, 18 years old looking to buy a car. Is your car as cool as this car right here? Yeah, good times. And now that you've read that, we're going to get right into it. Now, before I dive into it, I do want to point out that, like many AP exam questions, it is about 15 minutes per question. This question has some easy parts and some difficult parts, and when you're reading, A should be a pretty much of a gimme. B is also not that difficult. Now, this derive an equation expressing the velocity of the car's function in terms of k, f naught, and m. That gets to be a little tricky, and a lot of people will get stuck there and then just move forward. I do want to point out parts D and E you can actually accomplish, you can tackle without even doing part C. So for a lot of us, partial credit is going to be a way that we can earn 4s and 5s on that AP exam. This is definitely one of those questions where if you understand what's going on, specifically what I would say the most important part of the problem is part B. If you understand what we're getting in part B, you can easily do part A, part B, part D, and part E. Part C, deriving an expression, that is just screaming calculus right in your face. So now we'll get right after it. All right, so here we can see the question. Now, unfortunately, I can't get a lot on the camera at one time, so we're gonna have to, bear with us. Here we have the question, and right away here on this dot below, we want to draw a free body diagram with all the forces acting on the object. Well, we see the car sitting on the road, so right away you hopefully recognize we have the force due to gravity that I'm going to label mg, and as always we have a normal force n. Now, two other keys in this question is that it started from rest and there's some driving force, which implies there's going to be an acceleration. And that driving force is labeled as F naught. So I'm going to put that driving force here, label F naught. And since I am labeling that represents the forces acting on the car as it moves to the right, now that's kind of ambiguous. I'm taking this at a time t equals 0 seconds. And actually, I want to say a t, not t equals 0 seconds, I'm going to say just after 0 seconds. And the reason I'm doing that is because it's going to be my interpretation that eventually this car is going to stop accelerating. So based on my diagram, I want F naught to be bigger than kV, which is my resistance force, almost like my frictional force, and I'm labeling that kV. Now, it's my interpretation that I don't think you would need to do that, but based on their ambiguous directions, as the car moves to the right, at some point, those two forces are probably going to be equal and opposite. But based on B, determine the horizontal acceleration, well, I'm assuming they want me to show that this object is accelerating. And F naught bigger than kV shows that acceleration. Now, part B, as I said earlier, part B to me is really the meat and potatoes of this question, even though it is pretty easy. Determine the horizontal acceleration of the car in terms of k, v, and F naught and m. So I'm going to go right to my bread and butter of what I always love. I want to say the net force, that's supposed to be a vector, equals ma, where my net force we can see is obviously F naught minus kV. So I'm going to say F naught minus kV equals ma. I also want to go back up to this diagram real fast. Notice I did not label this negative kV, and hopefully you didn't do that either. They told us the resistance force was negative kV, negative indicating my direction. So this should be labeled as a positive kV in the negative direction. Hopefully you didn't make that mistake. going back to determining the acceleration, now I'm just going to rearrange. And I have acceleration is equal to F naught minus kv over m. That is my expression for acceleration. Now, these two portions are going to come into play a little bit later towards the end of our problem. Now, this is what I would determine as the most difficult part, but this is just going to be a straight mathematical part. Now, derive an expression for velocity as a function of time in terms of k, f, and m. So, I have this velocity here, but deriving an expression, I don't want to just rearrange and say v, because that's not in terms of t. What I do know is, what do I remember about acceleration? Acceleration, by definition, is just dv, that doesn't say dt, dv dt. So I can rearrange this, I can substitute, and I can say sorry about that, dv dt equals f naught minus kv over m. And we all know, those of you who follow some of my videos in the past, or those of you who happen to be in my class, know my calculus struggles. So if I can get through this, you can get through this. And I may do it a little differently than you, again, because of my own calculus deficiencies, but we're going to get through it one way or the other. So here, the first thing I'm going to do is I'm going to separate terms. So I'm going to say dv is equal to f naught minus kv over m dt. And now I want to bring this dv, I want these v's over here, and those things come together. Oop, I just knocked my whole camera. Those things have to come together. So I do have more paper behind this because I thought this was going to be long. I have dv over f naught minus kv equals, I'll just say dt over m, or you could also say 1 over m dt. All right, well, again, I want an expression for velocity. So eventually I need this velocity on its own, plus the fact that I don't like that I'm bringing this thing in where I'm trying to differentiate with, or I'm going to eventually not differentiate, integrate with respect to v. So I'm going to factor out a k over here, which is going to be a little bit weird, but it's just so I can get v by itself. So I'm going to say dv over, what is that going to look like? K times f naught over k minus v, that's right, equals dt over m. So that does look a little weird, but that is just easier for me. And now when I'm going to take the antiderivative, because I'm getting rid of this dv, I'm going to get rid of this dt, so I'm going to take I'm going to put in a different color, the antiderivative of, this is going to look a little bit, I think, more normal. I'm going to put 1 over k times f naught over k minus v dv, that's on camera, yes, equals to the antiderivative of 1 over m dt. So now that I just moved that over, I didn't change anything. Also, actually, before I do that, my limits of integration. Since I'm starting it at rest, I want to go from at rest to some velocity v, and I'm starting at some time 0 and ending at some later time t. So now that I have this, it doesn't matter if the dv is here or on top, I should recognize that this is a natural log, right? A dv over a v is going to be the antiderivative of that is a natural log. So to do that, see if I can get all that on camera. I don't have to rewrite it. Okay, I'll just rewrite it. I'm going to have the antiderivative from 0 to v of 1 over k times f naught over k minus v dv equals the antiderivative from 0 to t, 1 over m dt. Well, I like the right side because that side is pretty easy. And like I said, hopefully I'm recognizing the dv over v is going to be a natural log. So what is this going to come out to be? This is actually, what I'm also going to do is I can pull this k out because that's just a constant k. Yeah, I'm going to pull that k out and then multiply by both sides. So I'm going to have this over here. Right, I have 1 over k multiplied by both sides. So I'm going to bring that k over in this step. Antiderivative 0 to v, 1 over f naught over k minus v dv equals, I'm going to do that. The antiderivative of 1 over m dt is just going to be t, and I brought my k over, so I have a k t over m from 0 to t. When t is equal to 0, that's going to be 0. When t is equal to t, that's going to be kt over m. So the right side is going to equate to kt over m. That's easy. Now the left side, I like that better. Got rid of that k. That was a little bit confusing for me. dv over f naught over k minus v. That's going to be my natural log. So here I now have the natural log of f naught over k minus v from 0 to v. Well, again, now when v is v, I'm going to have f naught over k minus v. When v is 0, it's going to be f naught over k. And if I have the natural log of f naught over k minus v minus the natural log of f naught over k, that's when I'm going to evaluate that, right? This would be ln f0 over k minus v minus the natural log of f naught over k. That is the same thing as the natural log of f naught minus v, natural log rules, divided by, oh, sorry, I dropped, try that again, f naught over k minus v over f naught over k, all of that is my natural log, equals what I just determined, kt over m. Whew! All right, so now I need to get rid of my natural log. What is my goal here? Sorry, that's off the screen. There we go. What is my goal here? My goal is to get v by itself, so I'm going to kill that natural log. How do I get rid of that natural log? I'm going to raise both sides to the e. So now I'm going to have f naught over k minus v divided by f naught over k, all on screen, equals e to the kt over m. Let's see. Now I want to get this to the other side. So I'm going to multiply both sides by f naught over k. So I'm going to have f naught over k minus v equals f naught over k e to the kt over m. Whew, that looks like a bad, that's f0. There we go, f naught. All right, now I want v over there. I'm going to bring that side over there. So I'm going to add v and subtract that. So add v. So I'm going to have v equals, and subtract that to the other side, f naught over k minus f naught over k e to the kt over m. Now, if we remember, these are like time constants and whatnot. Those might help us for the last part, but we're actually going to avoid that because, again, I said I'm calculus deficient, and there's an easier way to talk about the graphs. Here I'm almost done. You may get full credit for this, but I can simplify. I can say my velocity is equal to factor out an f naught over k times 1 minus e to the kt over m. Whew. Welcome to calculus. So that is my expression for velocity. Now there were some spots where you can get some partial credit here. Go way back up here. If we recognize acceleration as dv dt, setting this up will get you some points. Setting this up will probably get you some points. And then from here it's just calculus. Now again, you want to be conscious of the time because that may not be necessary or even valuable enough for your time. Now the last parts. The last parts of this are two graphs, and I said we can do those graphs if I understood really part B of this problem. So sketch a graph of the car's velocity as a function of time, label important values. So I'm going to put an axis, and this is a velocity as a function of time. I imagine on the AP exam itself, the axis was already there. And I know the car starts from rest because they told that to me. And I know it's not a linear acceleration. I know that for a lot of reasons. I know that from what I just came out to express. I know that from my acceleration equation. So I know it's going to have some curve to it. And eventually, it's going to have an asymptote relationship. I need to expand that based on where it is. But I didn't label any important values. How do I know where that maximum velocity is? Well, let's go to the acceleration equation that we derived. F0 minus kv over m. Well, when we started, the velocity was 0. When my velocity was 0, I had an acceleration of f naught over m, which means I right now should have a what's it called? A known important value. Nope, and I just answered the wrong question. Hold on. Oh, I did. I'm sorry. Let's look at that again. I was thinking about part E. Ignore everything I just said. Let's solve for velocity. Velocity, this is a velocity versus time. Velocity is equal to A times m. All right, I'm going to tackle this a different way. I'm going to say that acceleration is f naught over m minus kv over m. That's okay. And now I'm going to see that my velocity is a minus f0 over m equals negative kv over m. A times m over k m over k times a minus f naught over m equals my velocity. I can distribute that through. I can say, oh, that's a negative velocity. I can say that, oh, you got off the screen. am over k minus f naught m over k equals negative v. Make that positive, make that positive, make that negative, and that doesn't actually matter. Now that my velocity is equal to this form, what can I say about my max velocity? When my max velocity, acceleration equals 0, that goes away, which means my expression for max velocity up here should be f over k, f naught over k. So my max velocity is when it is equal to f naught over k, and I should be able to see that also just straight from my picture, right? If this is a sketch of F naught and KV, right? When those two are equal to each other, so V equals F naught over K, V equals F naught over K. For part E, which is the part where I just got thrown off and I started answering by mistake, part E, sketch a graph of the car's acceleration as a function of time. Acceleration as a function of time. That should be a little bit straighter. Now, my max acceleration, I can go right to this equation. My max acceleration, if I just say A is equal to F naught over M minus KV over M. Max acceleration, I started from rest, which means it has to start from there. And my maximum value for acceleration is going to be F over M, right? Because if V is 0, that's where my acceleration is the greatest, which means this is not starting from 0, I'm lying, starting from there and ending at 0, so it should be kind of an asymptote that way. That is a very ugly graph. Try that again. I'm going to draw it in blue so it's easier to see. My acceleration as a function of time, be an asymptote that way, where this point should just be F naught over M. That is, as we can see, when velocity is equal to 0, my maximum acceleration will be F naught over M. So this was, especially towards the end, a little bit of a fumble. I apologize for that, but this is going straight at the problem where the difficulty is really factoring out or solving for V, but the rest of this should be pretty doable. So as you can see, questions like this are multi-layered, they're multi-tiered, they have some straightforward, do you understand what's going on, and then some complex, can I figure out what this integration is? Do not get stuck in the weeds. Have confidence you can definitely attack and solve these problems. Like you saw, if I can fumble my way through it, you definitely can fumble your way through it. In fact, you can get through it without fumbling at all. That's all I have for you on this version of Can We Solve AP Questions from the Past? If you're watching this on YouTube, by all means, feel free to like, comment, or subscribe, and you'll see me next time. Thanks for watching.